Getting recording and everything.
Yup. All right, and I'll pause it until. How's your day been?
Oh, tiring. Oh my goodness.
Real.
I had so much going on today.
How's
I
Chris?
even got a new
Sorry, what were you saying?
I went to the bank this morning and then I had an exam and then I studied for this coming up exam during my gap and then lab. Like it was so much.
Yeah. By the way, how was Chris Levy's presentation?
Oh, it was good, yeah.
Other than spilling much on herself.
Yeah, it was good.
How did everybody react?
No, everyone it was like an engaging conversation and two PIs actually had like a debate and they were kind of going back and forth and disagreeing. It was funny.
Oh shit.
That was cool.
Slay.
Oh, follow at Lisa the Spider on Insta.
Yeah, you should put one of her posts on your story or something. Damn,
Oh,
okay.
I don't even do my story,
I was making a joke.
as you could tell. I know, I know.
Actually, I wasn't. I'm not gonna do this unless you put a post on your story.
Do what?
The review session.
Oh my God, you're gonna kick me out of the review session.
I'll do more than that. I'm gonna kick you out of the class.
You know what? I don't want to take this class anyway. This is a requirement.
Girl, I'm just kidding. I know Henry's coming and I know Guillermo is coming. Let me call Najeska and ask her to call Guillermo.
Okay.
Hi. Hello, how are you doing?
Good, good in here.
Good. Can you do me a favor?
What is it?
You know our friend Guillermo?
Yes.
Can you tell him to join the Zoom?
There's a Zoom of what?
It's a review session for a class that we're both in.
Oh, oh, okay.
Yeah.
What is it like a e-board meeting thing?
No, but he said he was coming, so I want to make sure he can study and shit.
Okay, let me text him right now. So it's already started, like at 7?
Yeah, but so far there's only one person in. But I need at
Mm,
least like two people before I'm like, all right, I'm gonna start.
um, okay.
All right, thank you. Also, sorry for
All
being low
right.
key kind of sad. I'll tell you about it later.
Oh, it's okay, girl. You don't gotta apologize to me for being sad. It's okay, girl. Okay, I just texted him to. Yuzu told me to ask him to join, so
All right,
okay.
thank you, boo.
No problem. Bye.
Bye.
Bye. Oh, Nara, why you sad? What happened?
What do you mean? Oh, I don't want to talk about it.
Oh, it's okay. It's okay.
Nah, it's just I don't want to talk about it. But I want to talk
That's
about it, but I
okay.
don't want to deal with the repercussions of talking about it.
The repercussions, I won't like intervene. If that's what you're saying
Let's just
or
say
something.
I have a pretty good friend, I'd say. Not like
Mm.
a super close friend, but a pretty good friend who I've considered a pretty good friend, but I found out they do not consider me a friend.
Oh, that's rough. Oh, no.
Yeah,
Yeah, I'm sorry. That's so rough. I'm like, it's probably it's pretty up there for worst feelings.
right.
Not super, but that's pretty, yeah, not reciprocating, that's pretty rough.
Yeah.
Oh no. So what on the study guide do you think you need the most help on,
Who, me?
you think? Yeah, yeah, you.
I don't think I need help with anything.
Dang. Oh, you're just that smart, huh?
Well, this is my major.
Yeah, yeah. But
Hold on.
um
I think really the only thing is like the different types of isotopes and what they relate to, but I'm gonna create like a little mnemonic for it.
oh, just the memorization thing.
Yeah. Because like most of this stuff is review for me. Because
Yeah.
like the geologic history of Earth and evolutionary biology are like two of my like personal passions.
Hmm.
Yo, what's up, Henry?
Yo, my bad, I'm stopping, but I'm here.
Gay boy.
Yeah. Oh my.
Yeah.
Okay. I just unpaused the recording. I know Guillermo and Leslie might be coming. So yeah, in the
Yeah.
meantime, hold on, let me move this out of the way.
Fuck, did I drop it?
You guys can see my screen, right?
Yeah.
Yep.
Okay.
So,
Okay, so I still have the slides from last,
so
excuse me, I just got hiccups. From last exam. Do you want me to go over those slides as well, or do you guys feel like, oh, I did well on the exam, I don't need to do that?
I think briefly at the end do
Okay.
that, but if we have time, you know.
All right. So first let's talk about planetary origins and the early Earth. So The Big Bang Theory is an amazing sitcom from CBS. No, it's basically the theory, which in this context, a theory isn't just like like a hypothesis, it's a thing that has a lot of substantial evidence and fits within our understanding of the world. Just thought I'd put that out there. But anyways, it's a theory that the universe formed about 13.8 billion years ago, during the Big Bang, where there was a giant explosion of energy from a point that was so immensely dense. And there are two big pieces of evidence for this.
because your mom.
Bruh.
So there's two big pieces of evidence for this. The first one is the red shift, aka the stretching of light towards longer, redder wavelengths that suggest universal expansion. And if the universe is expanding, something must be causing it to expand. And also, it means at one point it was, it expanded from a very small point, thus Big Bang. And the other is cosmic microwave background radiation. Forgot to write the word background, my apologize. Background radiation, which is faint remnant of the radiation from the immense explosion of energy from the Big Bang. So next we have condensation theory. Condensation, clear. I'm sorry. I love that TV show. Anyway, so condensation theory is the major theory for the formation of the solar system. Not just our solar system, but a lot of solar systems. And it explains where hot gases begin to swirl, and through gravity they condense to become the sun, and then later the planets. We've seen this thanks to the James Webb Telescope and also just like detection from radiation, but some evidence within our own solar system that this is what happened and not potentially something else was the evidence of calcium aluminum rich inclusions in meteorites, which are some of the oldest found, excuse me, some of the oldest found solids that we found in our personal solar system, as well as chondrules. I don't know how to say this. I think it's chondrules. She said it like twice in class, but I don't remember because I was kind of not paying the most attention. But that's okay. That's okay. Just early solar nebula droplets and observations of disks around stars. Kind of seeing this like swirl of energy. That we've seen in other solar systems. And because of this, we can roughly date the solar system, our solar system, to be around 4.57 billion years old, give or take about 0.5 billion years. So the iron catastrophe describes how the molten iron core of Earth was formed and which essentially helped create the Earth's magnetic field, which, as you know, is very important. Without the Earth's magnetic field, there would be no life. So this resulted from excessive internal heat generated by radioactive decay from the aforementioned condensation, as well as the immense compression of accumulating meteors and meteorites, which had iron deposits as well as other types of stone deposits on them, which would be destroyed. And iron is often a more simple compound that a lot of these more complex stones would turn into given the amount of heat. In the same way you can like boil mercury, for example, and it can lose some electrons and slightly shift its state. That is beyond the point. Giant impact hypothesis. Okay, so like basic query, there is this planetary body known as Theia, which was roughly around the same size as Mercury or Venus, or between the size of Mercury and Venus, and it crashed into Earth, causing Earth to grow in mass, but also tilt slightly. Hold on, I forgot to add that. And tilt. And for Earth to begin, and the moon to begin orbiting Earth. So evidence of this includes the moon's, excuse me, iron pore compensation, because, you know, a lot of the iron ended up being on Earth, and the moon is kind of like a lot of little rocks that like kind of coalesce together, as well as the nearly identical oxygen and titanium isotopes with Earth's mantle that are found on the moon, as well as massive angular momentum of the Earth and Moon system. The fact that the Earth and the Moon itself are on a bit of a tilt means that something caused this. And Occam's razor, it makes most sense for it to be the Moon. Excuse me, I don't know why I keep it coming. The role of the moon. So the moon is a crucial stabilizer for Earth. It helps with controlling the tides. Oh my gosh, how are you? Get me.
Angelica, I'm doing good. I'm
Okay,
great.
okay. You haven't missed much, just Big Bang Theory, condensation theory, the iron catastrophe, and giant impact hypothesis.
Okay.
Um,
Albedo, greenhouse gas, and solar flux. You got it.
okay, okay. Do you want a rundown of these at the very end, or do you feel confident in all four of these?
We can do a rundown at the end.
Okay,
These
okay.
look, you have a good setup here. I like this.
All right, all right. Yeah, so the role of the moon. So the moon is a crucial stabilizing for Earth, as we mentioned in the giant impact hypothesis. And it helps keep the axial tilt of Earth. Additionally, its gravity pulls oceans into two tidal bulges, which creates high and low tides, which is necessary for just the functioning of the ocean as a capacitor of like biological life. So atmosphere origin. Again, this is a hypothesis, but it is the most credible hypothesis in the same way that the asteroid killing the dinosaurs is the most credible hypothesis for this extinction. But volcanic emissions made early greenhouse gas blankets, which would be expanded by hydrogen and helium, which solidified it until we have the modern atmosphere, basically. So continents origins. The original continents were thin and likely formed from underwater volcanic activity. If any of you know about the geologic composition of Hawaii, you'll know it just kind of spits out land every couple 100,000 years. It's basically like this, just on a much larger scale and over a larger period of time. But the Hadean period was a very long period, and so that's kind of just, it was very slow, but that's how we got like continental mantles. And the reason that they weren't immediately submerged is because of a unique property of water, that it's... Okay, Leslie.
Hey guys.
Okay, we're just on the first slide, so you haven't missed much. Excuse me. But basically, water of all liquids is one of the densest. For example, ice is, you know, water in its solid form, but because of the molecular structure of H2O, the solid form of water is less dense than the liquid form. And even though the land masses weren't made of water, they had a similar property where the land itself, like the mantle, the crust that was at the surface, was less dense than the ocean. So that's partly why that they didn't immediately submerge. And then heavy bombardment period is a period in the Precambrian, pre-Phanerozoic, where Earth was getting hit by a lot of rocks and meteors, which deposited minerals as well as the early forms of water, which over time helped make the conditions of Earth livable. Any questions about any of these?
Nope, all good for me.
You explained it pretty well.
Okay.
Yes.
Okay, we'll go on to the next slide.
Joke, I'm sorry.
Sorry for coughing. So the origin of life. So what evidence is there for when life evolved? So evidence comes from ancient rock formations containing microfossils and chemical signatures, such as carbon isotope ratios that indicate biological activity as early as around 3.7 to 4.1 billion years ago, but tends to be more on like the conservative estimate. Additionally, simulations also show that organic molecules could form under early Earth conditions, supporting the plausibility of life emerging around this time. So even though the Precambrian was not the most ideal for life, we have found in simulations that it is something that is possible. So for where, it's most likely in hydrothermal vent environments, which is supported by the evidence of chemical gradients and mineral catalysts that could drive the formation of polymers, lipids, peptides, RNA, and DNA. These environments also support the modern extremophiles and provide conditions for molecules like ribosomes to form and function. If you remember in class, in the previous unit, we were talking about how, like, hold on, actually, I think I can find the slide. Nope. Yes. So this one. So there's like photosynthetic versus chemosynthetic. Most chemosynthetic organisms originated from these volcanic vents, and the greatest diversity of different like synthetic organisms that can like turn different nutrients into energy and matter comes from these vents. So that's why it's most likely believed that it was these volcanic vents that is where life originated. So what are the characteristics of Luca? So Luca, also known as the last universal common ancestor, was most likely a single-celled organism with genetic material, probably DNA, but it might not have been DNA. It might have been like a proto-DNA-like structure, ribosomes for protein synthesis, and basic metabolic pathways. It was not alone because there was obviously other organisms that emerged during this time. It's just Luca was the most successful. And it represents the lineage that survived and gave rise to all life today. You can kind of see this where, especially within eukaryotes, almost all of them have a couple basic structures that are found throughout them, no matter how differently genetically diverse they are. And yeah, and then be able to, this is another question that was on the study guide, but basically be able to describe the importance of monomers, polymers, and lipid vesicles as components of cells. So monomers are basically small little building blocks that join to form polymers, such as proteins and nucleic acids, which are essential for structure and function of cells. Without these, the cell cannot have a border, which means that the cell cannot exist because without the border, it is just goo and it's not alive. Lipid vesicles can spontaneously form in these membranes because, again, the monomers which create polymers are partly created by these borders, which inside has the membrane. And so these lipid vesicles are basically compartments that separate internal chemistry from the environment, which was very essential for early life to develop and go from abiotic to biotic, essentially. So how oxygen changed the world. So in the study guide, it said you should know these. Oh, wait, before I go on, any questions about the origin of life? I'm gonna take that as a no. If not, speak now or forever hold your peace. Okay, so how oxygen changed the world. So, key terms that you need to know. Stromatolites. These are the layered rock structures formed by photosynthetic microbes and is the earliest evidence of oxygen production that we can find in the fossil record. They're mostly found, if you remember the map, they're mostly found in a few areas, namely Australia, part of Siberia, and part of Colombia, I believe. Don't quote me on that last one. Because of how fucking old these rocks are. But yeah, it's basically the earliest evidence of oxygen production photosynthesis. So obligate anaerobic and aerobic. So anaerobics cannot tolerate oxygen. Aerobics, on the other hand, can use oxygen for efficient energy production. A lot of anaerobics include these chemosynthetic organisms. Aerobics includes us. Yeah. So band in the iron formation, so alternating iron-rich layers also act as evidence of oxygen reacting with the dissolved iron in the ocean. If there wasn't any oxygen, these iron bands wouldn't be able to form. Therefore, we can deduce, yeah. And then eukaryotes versus prokaryotes. Eukaryotes have complex cells with organelles. Think a nucleus or a chloroplast or a mitochondria, which, as you know, is the powerhouse of the cell, or complex ribosome structures, etc., etc. Prokaryotes, on the other hand, are very simple and they lack a nucleus as well as fully functioning organelles. If you've taken any biology class, you probably remember the difference between the two of them. But you can just remember it as eukaryotes, like you, because you are a complex organism, versus prokaryotes, like protists, which is a very not complex organism. So what makes oxygen toxic and how have we been able to survive and use it for energy? So O2 forms reactive oxygen, hold on, I copied this from the textbook. I believe that says species, I might have gotten it wrong though. Also known as ROS, that damage cells and organisms such as fungi and animals. Why did I say that so weird? In animals, have evolved enzymes, for example, catalase in humans, to neutralize ROS and harness the oxygen for high energy respiration via the process of ATP. Basically, oxygen is toxic to us, but we have these proteins in our body and in our cells that are able to surround the oxygen molecule and make it so it's usable for us and so we don't die. So what does aerobic respiration and eukaryotes tell us about the history of oxygen? So it indicates that oxygen availability, mitochondria likely evolved from anaerobic bacteria. Endosymbiosis basically is where a larger single-celled organism ate the mitochondria, then got the powers of the mitochondria, for lack of a better term. Think of it like Kirby. That's also how it's believed that chloroplasts evolve, or not evolved, but became intertwined with plant cells, showing oxygen-enabled complex life, which is further proved by the fact that nearly all non-oxygen-based species are tiny microorganisms that live solely in volcanic vents. Again, where the most diversity is. We've talked about this 3 or 4 times. I feel like it's going to be on the question, just like what are the 3 factors? Remember, it's greenhouse gas, albedo, and solar flux. Again, I feel like she's going to ask for the most diversity of forms of life when it comes to stuff like this. Just say volcanic vents. I will have to go in a second just to pee. I drink a lot of water. But let me just finish the slide and then I'll be right back. So what is the Great Oxidation Event and what is the evidence for it? So around 2.4 billion years ago, rapid rise in atmospheric O2 due to early autotrophs, like we talked about right here with the photosynthetic microbes, created the Great Oxidation Event. Geologic evidence includes the banded iron formations and disappearance of reduced minerals, which the chemosynthetic organisms were using to create the energy. Biological evidence includes the expansion of oxygen-producing cyanobacteria, and isotopic evidence includes changes in sulfur isotope signatures as a result of the atmospheric O2. I will be right back, but before I go, any questions about this slide? or anything about this topic?
No, I'm all good.
All right, I'll be right back in like 2 or 3 minutes. So
Don't fall in.
okay.
How prepared are you guys for this exam?
Like
Uh,
50-50.
yeah, last
50-50?
exam, the only time I studied was the day before, which was this when she did this last time, and I did okay.
I mean,
Yeah, same.
honestly, the multiple choice, I mean, this is gonna help a lot. Especially with the like, I was really iffy about the short answer
Yeah,
questions, but
yeah, 60 was pushing it. Like a good thing is that there's 50 total or 50 multiple choice.
let me double check.
I think it's no, yeah, I think it's like 38 multiple choice and like 11 matching, something like
Well, it
that.
says 50. Well, it's right. 24 multiple choice, 11 matching, and then
What's the
four
other
short
one? I think
answer,
that's for short answers. Okay.
and then
Uh,
11 long answers.
what? Why is it four short answers and 11 long answers?
I don't know. That's they don't add up, but
I
yeah,
hope that's a typo. It's the other way
I hope
around.
so.
Real. Does anyone know like the how much the multiple choice is weighted?
Wait, I think it's two
Ver-
points each.
Two? Yeah, I don't
Yeah.
remember. Oh my goodness. But it's curved, so I'm not like too scared.
Okay, good.
And so after this one, it's just the final, right?
Yeah.
Yeah. Why is it
Nice.
two?
Do you guys even take notes for this class?
Oh, I stopped. Okay,
Barely.
Me neither.
so
You're looking at the notes.
I'm literally late like half of the time.
half of the time
Most of the time.
you're not even late. You're just not there.
Shut up.
You're just not there.
Oh my god.
You're trying to
Ah,
be so generous with yourself.
no.
So yeah, I mean this. I'm not gonna say anything, but you know, let's just hope.
Yo, is the final curved? Let me
That's
I
a good
check.
hope
question.
so.
It
That's my
should be
last final.
because
It's a 20.
why would she not though? Yeah.
Wait, what date is it? I didn't even check the date for it.
It's May 20th.
Oh,
May
the
20th. Ooh.
final will
Yeah, I
be
think that's
curved.
11:30 or 2:30.
Yay.
One of them.
Oh, okay, good.
Yeah, at least not Friday, like last time.
I'm so ready for summer.
Yeah. I'm at McDonald's right now. I'm at the drive-thru. Bless.
Oh my gosh.
Hey, he's got
It's
his
some
priorities straight.
no, it's large turkey, McChicken, and Papa Sunday. It's cold order, yeah. All right, thank you.
Okay, I'm back. Sorry about
I'm
this.
back.
Welcome back. Don't
Yay.
apologize for peeing. What the heck?
Okay, my bad. Um, did you guys like have any questions while I was gone, by the way?
We're just
No.
trying to shit about you, basically.
Oh, good things, I hope.
Yeah,
No, I
how
think we're talking
great of
shit.
a teacher you are.
Oh, thank you.
Yeah, right.
Okay, okay.
Yeah,
Unpaid
you're great,
TA.
amazing. Yeah, you should. You got TA qualities.
Yeah.
Oh, I've been a TA for like 4 classes before. That's why I'm good at this.
Oh
Oh,
shit, bless.
dang.
Yeah,
4 classes. Yeah.
botany 2 years in a row, uh, a statistics course, and a
Ooh.
international political thought theory course. Yeah. Okay.
That's
Um,
insane.
thank you. Yeah, since moving to Boston, it was like I didn't know any of the professors, so I wasn't offered any TA-ships, so I had like that hole in my heart. So last semester for art history, I was an unofficial TA for like 14 people, and now this semester, this one doing. But it works fine because like teaching material helps me study, so it's like a win-win.
Well, thank you. Yes.
You're a natural.
Thank you, thank you. Being a professor is like one of my dreams. So yeah. Anyway, so how life changed the world. So this first class, a question: how did the rise of methan methanogen, I apologize, English is not my first language, offset the weaker solar flux from ancient Earth, 30% less than we have today, and regulate Earth's temperature? So basically, methane producing microbes increased CH4, a strong greenhouse gas, which compensated for a fainter young star and kept Earth warm. That's basically just methane. And then how did the rise of oxygen reduce atmospheric methane, and how did this send Earth into an ice age? So basically, O2 reacted with CH4, reducing greenhouse warming and triggering a global cooling that likely caused the first ice age known as Snowball Earth event. So basically, think of it as this: methane goes up, there's more warming. Oxygen goes up, which causes methane to go down, which means there's cooling. Carbon burial means that the carbon is going down, which also leads to cooling because of the aforementioned process up here. So example of a positive feedback loop in this is methane warming equals more microbial activity. Because it's warmer, they're not freezing to death instantly, which means more CH4, which means more methane warming, and so on and so on. Negative is O2 rises, CH4 destruction leads to cooling, limits biological product except for those of the photosynthetic oxygen producers, which means O2 rises. Carboniferous period. So basically, a couple key things that you need to know here. There was rapid tree growth due to warm, wet conditions and the evolution of wood, apologies, and gymnosperms. If you need to know what a gymnosperm is, hold on. It's basically all spore-producing large terrestrial plants. So think cycads, ginkgo, pinus, sequoias, etc. If they have, I forget what it's called, like a pine cone-like structure to spread the seeds that they have from the spores, that's usually means it's a gymnosperm. They're really, really cool. Angiosperms are my favorite, but gymnosperms are also cool. Gymnosperms, they didn't appear in the Carboniferous period. I believe they started in the Silurian period, but the Carboniferous period is when they had maximum diversity. It is also when they developed wood, so they were able to be bigger and taller. And yeah, the CO2 decreased because it was stored in the biomass of these trees, because photosynthesis, CO2 is used in glucose. Wood takes up a lot more glucose than just a regular stem, which means that the oxygen was increased because of this enhanced level of photosynthesis. But because the trithivores or decomposers hadn't quite evolved yet for these changing conditions, because the conditions, of course, just changed, a lot of them just, when they died, they'd fall and be there. And that's why there's so much coal from this period, because, excuse me, there's so much coal from this period because it was when there was so much biomass that was unable to be decomposed, and when biomass is unable to be decomposed, it's turned into coal, or it's able to fossilize more quickly and then later turn into coal. But it was also during the late Carboniferous period that the first fungi that were capable of breaking down wood, lignin, increased, which caused decomposition of the dead plants, reduced carbon burial, and stabilized O2 levels, which brought us into the following period known as the Permian. And if you're wondering, that event is called the Carboniferous Rainforest Collapse, I believe. And it is, I believe, one of the mass, no, it's not one of the mass extinctions. I lied, my bad. But it's a minor extinction. So that brings us on to the Phanerozoic Eon, also known as the period of time in which life really started showing up in the fossil records, when we got distinct phylums that we can name, like chordates and arthropods and mollusks. Yeah. So Phanerozoic Aeon, a couple key changes that you need to know are some of the major mass extinctions. So there was the End Ordovician period, which Matilda, our group, discussed. Do you want to give a little TLDR of the End Ordovician extinction? If you don't, I can.
No, no, thank you.
Okay, okay. Basically, everyone here knows the process of eutrophication, right?
Yes.
Okay, so there was a lot of dead matter in the water, which led to a lot of nutrients in the water, which led to a lot of algal blooms, which led to the water becoming anoxic, which caused a lot of the keystone species, namely corals, and a lot of keystone microorganisms in the ocean to die, which had major disruptions across the food chain and led to a massive decrease in marine species because the water was toxic and the food chain was disrupted. The end Devonian period, I'm not sure how it ended. I can actually Google that real quick. Let's see. Uh, cause rapid global. Oh, so very similar to the Ordovician. Shit, I got the Ordovician and the Devonian mixed up. What I just said applies to the Devonian, not the Ordovician. Let me see what caused the Ordovician. Okay, yeah. Global cooling and global warming. Okay. Then the Permian was caused, I believe, by a volcano. Yep. And then the Triassic, I think that was also global cooling. Oh, off the volcano. And then everyone knows how the Cretaceous, that's the big asteroid. So again, to re-say, Ordovician was global warming, then global cooling. The Devonian was massive eutrophication on a planet-wide level. The Permian was a volcano. The Triassic was also a volcano. And the Cretaceous was a giant meteor coming to Earth. And then the Anthropocene, minor mass extinction has been caused by humans. A couple periods of extreme global cooling. There's the one that happened after the Cretaceous, which of course has basically existed for almost the entirety of the Cenozoic, and is part of the reason why mammals are so immense today, and why they're so, what's the word I'm looking for? So abundant. Because they had an advantage over their sauropsid counterparts by being able to adapt for colder climates. Then there was the one that happened at the end of the Carboniferous that we talked about here, with all the fungi evolving, and so there was reduced carbon burial and stabilized O2 levels. And then lastly, the one that happened at the end of the Ordovician that we also just talked about. Let's see, there's also tectonic plates, which I think everyone remembers from elementary school, but basically movement results in land being less dense than water, and global magnetic changes, shifts over time. Big thing you need to know is Pangaea existed for most of the Carboniferous, Permian, Triassic, and Jurassic, and then they kind of split apart. And then, yeah, a big thing that you need to know about ungulates. So at the end of the Cretaceous mass extinction, basically every single niche that was previously filled by the non-avian dinosaurs, as well as other large sauropsids like pterodactyls or mosasaurs, was quickly these available niches caused rapid evolution to fill them, which was mostly done by mammals, in particularly the ungulates clade, which is basically things that have hooves. Let's see. Climate change. Okay. So temperature, you need to know about oxygen isotopes. So basically, if there's more oxygen 18 than oxygen 16, that means there was more colder conditions. And if there's lower oxygen 18 than oxygen 16, that means there's warmer conditions. And these are found in marine fossils, such as of shells, of marine mollusks, and also some preserved exoskeletons of marine arthropods. And seeing the ratio between the oxygen 18 and 16 can help you see what the past temperatures of this period are. If you want a little mnemonic to remember it by, higher 18 means colder. So, when you turn 18, you kind of become more depressed. And then lower 18,
Hey yo.
when you're under 18, you're a bit happier. So it's a bit warmer.
Word.
Yeah.
True that.
Temperature changes for leaves in paleobotany. So leaf size and shape indicate climate. So larger, smooth leaves equals warmer weather climates. Think banana or plátano leaves. They're very large, they're very smooth, and they exist in very warm places like Miami or Dominican Republic. Um, yeah. On the opposite, ridges on leaves exist in very cold environments. Think of a holly bush. It has very sharp ridges, and holly is found in Northern Europe, the Slavic parts of the world, Canada, that kind of place. And yeah. Glacial periods. So dropstones are large rock deposits in fine sediments from melting ice. Delites are unsorted glacial sediments that have been lithified into rock. And then glacial striations are scratches on bedrock from moving ice sheets. Looking at these three things, we can see kind of additional indicators of glacial periods. However, these two are better for checking as well as this one. So changes in CO2. So yeah, as we know, more CO2 often means higher temperatures. Lower CO2 means colder temperatures. Paleosols are ancient soils that are preserved in atmospheric CO2 levels through mineral composition. And stable carbon isotopes such as carbon-13 and carbon-12 reflect changes in carbon cycling in the atmosphere. Higher C13 is linked to increased organic carbon burial and lower atmospheric CO2. So there's more 13, colder temperatures, because and if there's more 12, that means warmer temperatures. I can't really think of a mnemonic for that, just remember that. Okay, so changes in planetary energy balance. How do the following things affect albedo? Ice formation increases albedo because ice, for the most part, is white. And I'm talking both about the organization and the frozen water. And thus it reflects more solar radiation. Additionally, it leads to cooling, reinforcing. Oh, actually, before I go on to here, are there any questions from these last 3 slides that I forgot to ask if there were any questions for?
Yes, just one thing. So, you mentioned the anoxic ocean. So remember when Professor was talking about like the black shales?
Yes,
That's evidence of an anoxic ocean or like low oxygen in the water, correct?
correct.
Okay.
I apologize again. I always get the Devonian and Ordovician mixed up. I have since I was a kid. I do apologize for that slip up. Okay. So yeah, more ice equals wider surfaces, more warmth gets radiated back, which leads to cooling. We kind of learned about this first half semester. Volcanic activity. So ash and sulfate aerosols increase atmospheric reflectivity and causes short-term cooling by reflecting sunlight. But overall, on the long term, does increase temperatures, like on the long term. But this is just short term. Ocean currents. Actually, let me put a little star there. Ocean currents. So plate tectonics and basin changes. So redistribution of heat affects ice and thus albedo. Opening and closing ocean basins can enhance or reduce polar ice formation, which just goes back to ice formation. And the evolution of plants. So vegetation generally lowers albedo because they're darker than bare rock or ice. And forced expansion can increase absorption of solar energy, leading to a warmer effect. This is why tropical rainforests, despite just being on the equator, but this is like another reason why internally there's a lot of humidity, which leads to a lot of warmth. Yeah. Which is why a place like Miami, which is technically at the same altitude as parts of Texas, is a lot warmer than said parts of Texas because there's a lot more denseness of the vegetation, which creates a small localized greenhouse effect. Anyways, so how do the following affect atmospheric CO2? Volcanic activity releases CO2 into the atmosphere, just through the explosion, obviously, and contributes to long-term warming. So that's why I was like, here it creates short-term cooling by reflecting sunlight, but overall leads to long-term warming. That's also why you see in the mass extinctions that were caused by volcanoes that there tended to be the following period had a lot more warming than the period before. So the Permian overall was a very warm period, but the end Permian was a lot cooler than the early period. Then the volcano erupted, and then we saw in the Triassic a lot of warmth. And that's helped the sauropsids survive and thrive because, again, they're cold-blooded and are unable to regulate their internal body temperatures. Plate tectonics and mountain formation. Uplift increases weathering of rocks. Weathering removes CO2 from the atmosphere, cooling over long time scales. Yeah, and then evolution of plants. Plants absorb CO2 via photosynthesis. Expansion of land plants significantly reduce atmospheric CO2. And then burial of organic matter locks carbon away long term into like coal and natural gases. Any questions about changes in planetary energy balance? Okay. The Pleistocene, part 1. So yeah, Pleistocene, just think of it as everyone's seen the movie Ice Age. That was the Pleistocene. We got Manny, Diego. I don't see Sid. I'm sorry. I know I should have chosen some art that had Sid. I'm a fake fan. I love you, John Leguizamo. I swear. Okay. So evidence for recent ice ages on Earth. So glacial landforms, such as moraines, which is ridges of deposited debris, and drumlins, steam tails of glacial sediment, indicate past ice movement. Additionally, if you look at where predictions are of where glacial ice would have been, there is weird freshwater lakes in every single place where glaciers used to hypothetically be, which is additional evidence. I didn't mention that here, but I just thought I would real quick. So tillite, which I think we discussed in a previous slide, is liquefied glacial till and drop stones, large classes of marine sediments, provide geologic evidence of ice rafting in deposits, and then ice cores in places that have been covered in permafrost for several millennia. And marine sediments can show cyclical climate changes consistent with Pleistocene glaciation. So basically, we know a lot about the Pleistocene glaciations because it was, only 50,000 years ago. And so by looking at similar patterns to the ones that we were able to very clearly see in previous periods, we're able to predict that there were other ice ages. So the Milankovitch cycles and planetary energy balance. I will say, out of everything we've covered this semester, the Milankovitch cycle is the thing I'm least confident in. So if you know a lot about this, please correct me. But basically, it's just the altering of incoming solar radiation, also known as insolation. And yeah, it's primarily influenced by the distribution of solar energy, so seasonal and latitudinal, not total energy. Depending on the tilt or the axis of the Earth, there can be more ice, which can lead to more albedo and a cooling effect. And then eccentricity alters Earth-Sun distance, obliquely changes tilt, and precession shifts timing of seasons. So predicting of seasons and climates for Boston, which was something that we discussed. High obliquity means more extreme seasons, warmer summers, colder weathers. Precession determines whether northern or hemisphere summers occur at the Perlian or Apollyon. I don't know how to say either of these words, but basically the poles have flipped a couple times. So right now it's spring in the northern hemisphere and fall in the southern hemisphere. But in other period time or in other past times where there was a different precession, they might have swapped. And then high eccentricity amplifies precession effects, which creates stronger seasonal contrasts. And then in Boston, cooler summers favor ice growth, warmer summers promote melting. Kind of self-explanatory. If you need to remember it, remember 2015 or 2017, I don't recall which one. There was like ice buildup in Boston for like until July or something like that. And it was like a big problem. So Milankovitch cycles and glacial cycles. So cycles influence summer insolation at 65 degrees north critical for ice sheet growth and melt. Again, that's where most of the glacial ice is. Think Canada, Northern Europe, Russia, etc. Low summer Greenland. Low summer isolation typically means that snow persists, so ice sheet expands and there's more albedo. High summer insolation means there's more melting, ice retreats, lower albedo, more warmth. Both of these are positive feedback loops, but they are dependent on the Milankovitch cycle, and so that's what decides if it's going to be which one of them, you know? And then ice albedo, that's what I just said. Types of Milankovitch cycles. There's eccentricity, which is the shape of Earth's orbit, whether it's circular or elliptical. Then there's obliquity, also known as tilt. Oh, and that changes roughly every 100,000 years, which is the tilt of the Earth's axis between roughly 22 degrees, 22.1 degrees and negative, and 24.5. So this change in tilt will affect how extreme the summers and winters are respectively. And then that changes every 41,000 years roughly. And then there's precession, which changes every 19 to 23,000 years, which is the wobble of Earth's axis, which will alter the solstices, so when the season starts. So yeah, precession is the extremity, or sorry, apologies. The tilt/obliquity is the extremity of the seasons. The precession is the wobble of Earth's axis and the timing of the seasons. Then the eccentricity is the shape of Earth's orbit, which is kind of the length of the seasons, for lack of a better term. Pleistocene glacial cycles as equilibrium, so climate oscillates between glacial, cold, high ice, high albedo, and interglacial, warm, low ice states. These transitions were driven by the Milankovitch cycle, amplified by feedbacks. So the albedo, CO2 changes, and these shifts reflect tipping between the two semi-stable climate equilibria rather than a gradual linear change. So it's like going from one extreme to another rather than it slowly changing over time. And that's why the Pleistocene was so weird. And then she said, for your group projects, make sure you know about them, so you can study them and be able to talk about the case studies that are within them. Our group did radiocarbon dating, carbon isotopes, and the Devonian mass extinction, not the Ordovician, the Devonian. And so yeah, I kind of already spoke about this, the eutrophication times 100, for lack of a better term. Does everyone here feel confident in the group project stated, or do you want me to go over the ones that me and Matilda and other people did as well?
Nope.
Nope, you are not confident in the presentations you did, or nope, you don't need me to do?
No, go over. No.
Okay. Don't go over, do go over.
Yes.
Bro, which one?
I mean, I'm good. Do not. That's me.
Wait, is
Okay.
it just like broadly knowing the terms like radio? Like obviously everyone did their own separate,
Yeah, so
mass
basically
extinction or
it's
carbon isotope. So
yeah, basically it's knowing, because I'm assuming it's going to be, she's going to ask 3 short answer questions where it's going to be like, what type of dating method did you do? Can you explain it in a couple sentences? What type of isotope did you do? Can you explain it in a couple of sentences? And what mass extinction did you do? Explain it in a couple sentences. So just being aware of what your group project did, or just being aware of another example. If you're like, I don't really understand my group projects, but I don't know, Leslie's group project was amazing and she talked about carbon isotopes in a way I thought I could never understand, and it really clicked in my mind. So just making sure you know at least one case study for each.
okay, got it.
Yeah. Were there any questions for all of the material for exam 2? Any of these concepts.
No, this is recorded, right?
Yes.
Okay.
Yeah, you're uploading this, right?
Yep.
On white.
Uh, on YouTube, probably.
Probably.
Yeah. Actually, since I'm uploading this on YouTube, I'll just also send the link to the first one that me and Henry did for the previous material. But before I do, if there's any like really specific questions about any of these, let me know. Where it's like, oh, there's just one thing from the first unit that you're confused by, or I can help explain, let me know. If not, if you have any questions, you can look at the other video.
Okay.
So are there any final questions?
No.
Okay. Oh yeah, everyone, make sure to follow Lisa the Spider. I know you all follow her, but in case people are watching the recorded version, make sure to follow her. Yeah.
The ultrasound one is sending.
Right, bro. Okay. In which case I'm going to go. I will upload the video on YouTube soon. And thank you everyone for coming.
Okay, thank you.
Thank you
very
for
much.
Thank you,
helping
Angelica. You're the
us.
best.
Yay!
Of
Yes,
course.
thank you.
I'll
Thank
also send
you.
the slides if you guys want to consult them.
Oh my
Yes,
gosh,
please.
yes. I need.
Okay. All right, thank you.
Okay, thank you. Bye.
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 Bye bye.